Okay, so my first question is 3.3 number 4, and I'm gonna work using Kramer's rule. So the first step is to view this system as AX equals to B, and then the matrix, first step we take the matrix out, minus 5, minus 3, 3, minus 1. This is our main matrix. And then we have to do A1B and A2B. So when we take those matrices out, A1B becomes 9 minus 5, 3 minus 1. And A2B becomes minus 5, 30, and 9 minus 5. After getting these matrices, we have to find the determinant for all of them, for the first matrix, second, third matrix. So for the first one, for A, determinant of A becomes minus 5 times minus 1 minus 3 times 3, which gives us minus 4. So the determinant for A is minus 4. And next we do determinant for A1B. That becomes 9 times minus 1 minus 3 times minus 5. This will give us that A1B, which is equal to 6. For the third one, we get minus 5 times minus 5 minus 9 times 3. This gives us minus 2. This is that A2B. So the final step for finding the solutions for this question is for x1, which is the first solution, you take determinant of A1B divided by determinant of A. So we've already found 6 for determinant of A1B, and determinant of A is minus 4. So we have minus 3 over 2. And x2, which is related to determinant of A to B, over determinant A, which is minus 2 over minus 4, which is equal to 1 over 2. So the solutions are minus 3 over 2 and 1 over 2. So we solve this system by using Kramer's rule. So the second for this question, we have to find a specific example to prove that W is not a vector space. So we are going to try to find some example that's going to prove that. So let's just late A and B, B1, because we can't let anything for these values. So 1 plus 1 plus C equals to 0. 2 plus C equals to 0. In this sense, we can find C to be 0. So for the first solution, we have 1, 1, 0. In this case, this is valid, so we might say it's a vector space. But let's try by multiplying this whole column or matrix with some x, and then let's see if that's going to be valid. So let's multiply it by 3, for instance. So if it's 1, 1, 0, when we multiply it, it becomes 3, 3, 0. So in this case, A is 3, B is 3, and C is 0. So when we make cross-check this with this equation we were given, 3 plus 3 plus 0 equals to 2. This is 6 plus 0 equals to 2, which says 6 to be equals to 0. But this is not a valid answer. So from this we can say, since this doesn't work, or since 3, 3, 0 is not included in W, this implies that W is not a vector space. Yeah. So we have given an example which is 3, 3, 0 for ABC, and we have proved that W is not a vector space. So that covers the foregoing number 7. So this question asks us to find the basis for the null A and call A of the A matrix here. And this B is the row equivalent, like the reduced matrix of A. So whichever works for B means it goes back that it works for A. So this is easier to do because it's a row equivalent or a reduced matrix. So we are going to use this one to find the null A and call A. So first I'm going to start to find null A. So when we look at this one, when you try to do null A, you equate everything to 0. So you add a 0. That means 1, 0, 0, 0, 2, 0, 6, 5, 0, 5, 3, 0, and then you add 0, 0, 0. And then you write the equation from this one, from the matrix. x1 plus 6x, since we have x2, 0, we go to x3, plus 5x4 equals to 0. For the second, we don't have x1, so we have x2, 2x2, plus 5x3 plus 3x4 equals to 0. And for the last one, we don't have anything. That means for x3 equals x3. And for x4, since we don't have anything, x4 equals x4. This implies that our x3 and x4 are free variables, or free. So we can assign anything, but we have 3 equations for x1 and x2. So for x1, we have minus 6 x3 minus 5 x4. And for x2, we have 2x2 equals minus 5 x3 minus 3 x4. And when we did like this one, it becomes minus 5 over 2 x3 minus 3 over 2 x4. And for x3, we have just x3. And for x4, we have x4. So when we rewrite this as a solution form, we have x1, x2, x3, x4, which is going to be equal to minus 6 x3 minus 5 x4, which is for x1. And for x2, we have minus 5 x3 minus 3 x4. For x3, we have x3. For x4, we have x4. So when we write the final answer, it becomes x1, x2, 3, x4 equals x3 into minus 6 minus 5, 1, 0. And for x4, we have minus 5 minus over 2 over 2 minus 3 over 2, 0, 1. So this is our u, this is our v, and the basis for null A is u, comma, v, which is, in this case, minus 6 minus 5 over 2, 1, 0, comma, minus 5 minus 3 over 2, 0, 1. So we found the basis for null A, and minus 6 minus 5 over 1, 0, minus 5 minus 3 over 2, 1, 0. This is for null A. So the next part is finding the call A of the same question. Call A. First, we see the pivot columns. Here we have one pivot and we have one pivot and we don't have any. So these two are non-pivot columns. And these non-pivot columns are usually they're made by combining these other matrices, columns. So let's see for this is B1, this is B2, for B3 and B4. First let's find what B3 is composed of. And it is B4 plus B2 plus B1 If we equate that, we get B3. So it's made from other columns. And for B4, we have B3 minus B1 minus B2. This means these two are not independent. They are dependent on the other columns. And by using the spanning set theorem, since these two are not independent, we can cancel them out or we can leave them alone. And we'll be left with S equals the first row, which is B1, 1, 0, 0. And then the next one, B2, which is 0, 2, 0. So, in order to say S is a basis for call A, we have to make sure B1 is not a 0, 0, 0 matrix column. Then, since we have one, it's not, so that's checked. And we have to make sure both of them are linearly independent, like one is not made of the other. And then when we check, it doesn't come like that. So, this one is also checked. So, from this, therefore, we can say S, which is 1, 0, 0, comma, 0, 2, 0, which is B1, and B2 is a basis for call B. But we are asked to find call A. But since this is a row equivalent of matrix A, we can say B1, A1 and A2 are the basis for the null A. So we say minus 2, 2, minus 3, 4, minus 6, 8 is